So here we are, and now that we've built Butterizer, we're going to go ahead and do a few tests on it. Of course, the idea is not just to build the thing, but to sort of give it a bit of a characterization and kind of understand how does it behave. You know, what does it do? How does it react in certain circumstances? That kind of thing. So it's a DC to DC converter. So of course, the most important thing is, well, how does it perform as a DC to DC converter? Right? Do we, you know, obviously part of this architecture is to basically have a switch that's basically switching on and off really quickly, which is what the FET is inside here. And yeah, and of course that's going to create noise and all sorts of other stuff. So we want to see, of course, we're going to want to see how bad that is. So we're going to want to measure that, and we're going to want to do that under various loads, because of course, you know, just plugging this in and, you know, firing it up and having a voltage across here, across the outputs here is, you know, kind of useless if it's just open circuit like that. I mean, yeah, sure, it might measure 5 volts or whatever, but who the heck cares, right? Or 3 volts or whatever, but who cares? What we're really interested in is when we put a load on the output, what does this guy start doing? Does it start, you know, does the noise increase? Is there more ripple? Is the voltage drop? Does the output not go to a very high current? I mean, those are all, you know, are as high current as it could. So these are all things we're going to test. So we'll start off with the basic test. The first one is we'll plug it in, leave this open circuit, and just do a quick measurement across here. Make sure that we have the expected voltage, and then we'll go and proceed to do a test under basic load, and then sort of get a feel for how it works. So let's go. I'll go set that up and walk you through the setup. And we'll take a few measurements. All right, and here we are. We've got the setup here. It's a very basic setup. We're only going to do a couple of really quick measurements set up like this, and we're going to convert it a little bit. But we've got the Butterizer right here. I got the inputs flipped over. So this is the output here, pardon me, and this is the input. The input, of course, we're going to set it to 1.5 volts. And we will measure the output. But again, this is, let's put this back a little bit here. Maybe tilt that down a little bit. There we go. YouTube, awesome framing, right? So, of course, this is the open circuit. This just has the internal resistance, which is like 10 meg or 11 meg of this multimeter across the output. So, of course, it's going to basically, you know, almost zero draw on this power supply, but that's okay. We're just going to check to make sure that it actually can meet at some point its rated output spec, which again I believe is 3 volts. I could be mistaken. It could be 5. I don't remember. So we'll see. So let's go turn that on, and of course we're going to get the output readout here on the DMM, and we will turn this up to 1.5 volts. Oh, that's right. Never mind. Yes. Okay. So this is a boost converter, of course, right? So this is going to take a input voltage of up to 1.5 volts down to, or I should say, from 0.6 to 1.5 volts, and boost it to 1.5 volts. So of course, as we go down, our output is still staying at 1.5 until we hit about 1.6, 1.5, and then the output starts collapsing. But surprisingly enough, an open load, or an open circuit, pardon me, it's still holding 1.4 volts at 100 millivolts. That's pretty impressive. Anyway, so we'll go and bring this right back up to 1.5 volts here. We'll make sure the current limit is set for something reasonably high. Doesn't really matter what it is, because I don't think this thing does more than an amp. I could be wrong. And so right now we're measuring our output voltage. That's good. So the next step is to go ahead and apply a load and see whether or not, as we increase the current draw on this, it can maintain its 1.5, roughly 1.5 volts output voltage. So be right back. All right. So now we've got the setup changed a little bit. So we still have our DMM in measuring across the outputs, and in fact, it's going to actually measure across the load points on the electronic load that I've set up here. Normally, you also want to measure the drop of the cable here, so you would normally probe right here, or even better, right here, but we're not measuring with a battery, we're talking about a perfect current source here, so it's not going to be much of an issue. So we'll probe across here, mostly just to show you what the voltage is here, so I can have both readouts here, both the current and the voltage simultaneously. So what we'll do is we'll turn this on. So we've got our voltage there, and of course, again, the load is measuring the voltage across the input terminals as well. But we'll set that to current, 1.5 volts there. All right. So what I'm going to do is, as I turn up the load here, what's going to happen is, of course, the voltage should hold at 1.4 volts. And what we'll see, we'll basically dial up to 100 millivolt. We'll do 50 milliamps first, then 100, then 200, then 300, 400, 500, so on and so forth, and see where the output voltage starts collapsing. Don't forget, the input voltage should not collapse. If we're running a real battery, however, it probably would at some point, because we'd be asking for too high a draw, and it would just start shorting the battery. Well, not shorting, but we'd basically take too high a draw from the battery. So we're going to go ahead, I guess we're going to have to turn the load on, and we'll turn that up to 50 milliamps, and so far we're doing just fine. And just for fun's sake, we're using about 60 milliamps, 60, 70 milliamps. Now I'm not entirely sure if these are both calibrated with each other, so let's say it's about kiff. So let's bring that up to 100 milliamps now. That's not too bad. So we're still at 1.4. Let's bring that up to 200 milliamps. It dropped a little bit, but yeah, it might also just be error in the last digits. So let's bring it up to 300 milliamps. It's starting to drop a little bit again, but still holding. 400 milliamps, we're still good. Half an amp. And now this is where we're starting to see the major difference. So the draw on the power supply on the current source is now actually at 3/4 of an amp. So we're actually burning roughly 30%, 33% of our energy just doing the conversion, the boost, which, you know, considering we're running at 1.5 volts, it means that basically we've got some loss. We'll obviously have some losses here. So let's bring this up even higher. Let's see where this starts going. Oh, and that is that. So we're using about an amp now, and we've topped out at roughly 660 milliamps, pardon me. But our voltage hasn't collapsed, it just doesn't want to go any further. So let's turn that off so we don't stress Butterizer a bit too much. So what have we figured out? What have we learned here? Well, we've learned that at 1.5 volts on input, keeping our 1.5, it was 1.49 something, like 1 or something like that, but keeping basically our 1.49 volts output, we were able to hold an output current of about 650 milliamps, which is not bad with a input current of approximately 1 amp. All right, so now we are going to run our next test, which is our noise measurements. So we've already ascertained about how much load Butterizer can sustain on the output. Ideally, we'll look at the cutoff voltages too, so you know what can it do under load. But we're going to do a quick noise measurement first, since I've got everything set up. And what we're going to basically do is we're going to do, again, the same kind of thing, a noise measurement with essentially open circuit, and then we'll do a noise measurement under load and see what we can compare and contrast the two. So what I've done is, the setup is really straightforward. I know you're not really supposed to use 10x probes for this, but I'm just going to go ahead and use one anyway, just because that's the way I have it set up. And in any case, we're going to look at some relative measurements. We're not looking for absolutes here anyway. We're looking at how much more noise are we going to have. But the interesting thing here is that, of course, we're going to have the probe set up, probing directly at the output, or the input of the DC load. Sorry, and we've got it grounded here. So, and if we go just look up here, haha, there we go. So now we've got our scope. What we'll do is we'll set and configure this for, oopsies, pardon me. So we'll set this for AC coupling. We'll turn the bandwidth limit on, and of course it's a 10x probe. I'll set it for 1 meg input impedance, and let's go take a look at the triggering options. So here we're going to look at edge triggering. Yeah, why not? We'll do edge triggering on channel 1. Slope we'll do either or. Setting, we will AC couple that. I'll leave the noise reject off and leave the hold off as it is. Sorry, my hand's in the way. Okay. So now we'll set up, and I've set up the vertical division for 500 millivolts per division. Actually, we're going to bring that down a little bit more. Bring that to, well, we'll bring that to 100 millivolts per division. But that may not be enough, but we'll see. So I'm just going to reframe this a little bit better so you can sort of see what's going on here. Oh yeah. So, and right now, so everything's off, and there's a little bit of noise. I believe those are my lights. There's probably some other crap going on here anyway. Probably common mode noise. Anyway, not going to worry about that. So there's a little bit of noise, so if you can see it, if I crank that up, that's all this crap here. Some high frequency noise. So we'll keep that at 50 millivolts per division actually instead, because I think the ripple shouldn't be much worse than this anyway. Much worse than a few divisions at 50, so a couple hundred millivolts, worst case. In fact, it should be a lot less than that, given it's only 1.5 volt output. So let's go turn this on. So this is no load. We're going to turn Butterizer on. Well, that's already promising. So we've got our 1.497 volts out, and as you can see, there's almost no noise, which is great. That means there's zero leak through when there's no load, which I would have expected. I would think it's a pretty crappy switcher if there was noise when it wasn't turned, wasn't sourcing current. So what we're going to do is we're going to turn down the load again. So we're drawing almost nothing. We'll turn the load on, and we'll go and draw 50 milliamps. Turn that off so you can see. Let's set up a measurement here. Let's look at the peak to peak. So the peak to peak right now, and I'm going to turn measurements, statistics on. Okay. Okay. So we have our peak to peak here, and we're looking at a peak to peak of roughly 30 millivolts. If I turn that off, it's hard to tell. So that's really within the noise of the setup, I think. I'm going to go down a little bit further, but there's not much more we can do about this, unfortunately. I'd have to try and track down where that's coming from. But it's highly likely it's coming through either the power supply that we're using. Oops. Works better if you ground it. Hang on. There you go. Or maybe some sort of radiated source that's being picked up on one of the cables. Some inductance in the cables and they're acting like big antennas. Could easily be it. And if I fiddle with this, I'm getting a little bit. So anyway, okay, so let's ignore that for the moment. I'll bring this back down to about 50 millivolts per division. And I'll turn it back on. So now we're pulling, or drawing, I should say, 50 milliamps. So let's bring that up to 100 milliamps. Okay, so now we're comfortably over the noise, the noise floor, and you can see that. We're going to turn that off. You see, okay, so here's an interesting thing. So what I'm going to do is I'm going to put in a frequency measurement here as well too. So we're going to see if we can't try and capture that. So turn that on. Okay, so now we've got our noise here, and the difference is 33 millivolts versus 20 roughly. So yeah, so we're getting about 10 millivolt peak to peak ripple. That might be very difficult to measure in this setup, so I wouldn't trust it horribly, but there's definitely a little bit going on here. But what's more interesting is this noise here. Now this is it's having trouble picking that out a little bit, but let's see if we can't try and get this out of the noise. So it's in the ballpark of 190 kilohertz. So now I would be willing to suspect, I haven't looked, I don't remember what the data sheet says, but I would be willing to suspect that this is our switching frequency. So if we just play around here, we can see that it's roughly a division and a bit. So our noise here, our peak to peak, which should be here at any, here, it's about 12 millivolts peak to peak. 25 millivolts peak to peak. Unfortunately, this is probably just measuring right now this part in here. So if you look at this, we have that switching noise is looking at least 20 millivolts peak to peak. So let's go ahead and wind the wick up a little bit, and let's go to 200 milliamps. Oh yeah, now that's a good solid, 1, 2, let's say 2 and almost 3. So that's close to 56 on the dot, 56 millivolts peak to peak of noise. Just bring that down a little bit here. All right, so let's bring it up again to 300 millivolts, 300 milliamps, pardon me. There we go, and we've increased again, so we're now 80 millivolts peak to peak. We're going to turn that down a little bit. So our vertical division, our vertical scale now is 50 millivolts per division. So let's bring this all the way up to, let's bring this up to half an amp. Okay, so at half an amp, we're talking about 140 millivolts of peak to peak noise. Now again, I'm not entirely sure there was any suppression circuitry on this thing. Some anonymous bastard didn't probably add anything in. I think he just basically used pretty close to the reference circuit, and I don't think there's any dampening on that. Oh, there probably should have been, but anyway. So this is definitely coming through. So this is definitely the switching noise is leaking through, but that, that's okay. So let's bring this all the way up. Let's go. Whoop. Ooh. Okay, we're now pulling 0.7 of an amp, and we're getting about 200 millivolt peak to peak. So that means on our 1.4 volt output, almost a seventh of that is noise. Well, we're getting a seventh of that output scale is noise, which is pretty not good. So we definitely, if we were to build a sort of a real circuit out of this to be used for something, we'd probably. I'm just going to shut this off. Actually, what I'll do is do this. I'll do a single capture and then turn that off. Okay, so oh, that's cute. 200 millivolts on the dot. How fortuitous. So if we're going to build a real circuit with this, we probably want to have some sort of noise suppression circuitry filtering going on right after the output, just to sort of knock that down a bit. Maybe another cap or something like that, some sort of filter that would get rid of that. But so far that I can see, looks fairly good. A little bit warm, but nothing major. So that's cool. So what we're going to do is we're going to save this as a reference. So this is 1.5 volt input at full load, which is about 700 milliamps or something like that. So what we're going to do, we're going to save that as our reference. So now we've got our reference there. Start that running. We'll turn our reference off. So the next test I'm going to do, we're going to go ahead and we're going to bring, what we're going to do is we're going to take the same parameters. So if I turn this on now, we're about 680, 690 milliamps. Okay, so what I'm going to do is we're going to run this test, but we're going to take the input voltage down, we're going to wind it down. So we're going to run it at maximum load that we're able to, and bring the input voltage down. And we'll see, pardon me, we'll observe how the noise changes, reacts to that. Okay, so let's turn this on. There's our noise, and I'm going to bring this down. It's at 1.5 volts in input. I'm going to bring it down to 1.2 volts. And as you can see, we're at 1 volt. So as we go up, the waveform is also changing. So this is, as you can see, the switching frequency is changing in various other bits, as well as the amplitude of the switching frequency. So now we're at 180 millivolts peak to peak noise. Let's bring this all the way down. So we're going to bring this down to 6. See, okay, now here's something that's interesting. So I'm going to turn this off. So resetting everything, I'm going to actually point down here. So if we look what's going on here, all right. So again, we have our input voltage of 1.5 volts. We've got our output voltage here. We're going to turn that on. So everything looks good. Everything looks hunky-dory. We're going to start winding the wick down a bit. And as you can see, at about 0.9 volts, it starts collapsing completely. Like really badly. We're starting to get 1.3, 1.35. We're at 0.6 volts now. We've collapsed to 1.3, and now, boom, we've lost it. We've lost it all. So under load, this thing goes to maybe 1.5 volt. Maybe. And if we look up here, we want to... Oh, that's not fun. What's going on here? These alligator clips for these Rigol probes are horrible. Absolutely horrible. Alright. There we go. Alright. So let's reframe that a little bit. Okay. So on this test, you can see, well, it doesn't even want to, can't even start at 0.5 volts. There we go. If we bring this down to 0.8 volts, yeah, look at the noise here is, it's still pretty bad. That's about a 200 millivolts. So actually, interestingly enough, the noise doesn't seem to change a huge amount with the input voltage, which is kind of neat, which means that the output noise that we're filtering here, in terms of the frequency, because that's the thing I should probably be checking right here. And the frequency is bouncing between... Yeah, I mean, we're talking about 925 kilohertz down to approximately 900 kilohertz. So you're talking about filtering a band of approximately 30 kilohertz, maybe a little bit more depending on how things are going. So all in all, is really interesting. So we've done a few things. First of all, we measured the Butterizer just in open circuit. We verified that it can hit its 1.5 volts under no load, which is good. We also verified the maximum. Pardon me. We may verified the maximum current it can supply before the output voltage, or before it just stops, and before the physical circuitry on it can't give you any more current. And that was approximately 650 to 700 milliamps at 1.5 volts input. Then we went ahead and started measuring the noise, and the noise on no load, under no load is nothing, which is good, and under full load at 1.5 volt input, it's approximately 200 millivolts per peak to peak. Pardon me. And of course, the really good thing is, now if you bring the input voltage down, so that was again at 1.5 volt, but if you wind it down to 0.6 volts, you're able to stay within regulation, so within about 1.4, 1.45 volts output, but your turn this back on, but your noise, your output noise is still approximately 200 millivolts peak to peak. So that's fantastic. That means that with the proper output filtering, you're filtering approximately you're doing a filter on approximately 900 kilohertz to 960 kilohertz, and the amplitude, the amplitude of the noise is roughly the same. So you don't have to worry about putting heavy filtering or whatever. It should be relatively easy to filter. What we're going to do now is a quick temperature test measurement. So I'm going to go ahead and turn my big lights back on. So this is just a simple infrared temperature probe. I don't have with me a really awesome FLIR. That would be really cool. We have one at work, but I don't actually have one here in my lab at home. So what we're going to do is really straightforward. We're going to turn this sucker on. We're going to try and draw as much current as we can out of it at maximum input rated input voltage, just so that we've got the best chance of getting this thing as hot as possible. We're going to go ahead and measure it, and of course there's a little parallax error here, so we'll try and do our best here, but we'll go and measure that and see what this guy can get up to. All right, so let's go ahead and do that now. Turn that on. So we're pulling again you're drawing roughly about 700 milliamps. Right now we're looking at roughly about 30 degrees Celsius and rising. 31. Let that run for a little while, and we'll be right back. A few minutes into this test, and we'll go and do another quick measurement. So we're above roughly 45 degrees Celsius. And that's been rising, so that's roughly about several degrees per minute. I'm not entirely sure it'll continue going up, but it doesn't look like it's going to stop for any particular reason. So we'll leave it go for another minute. I think I'm only going to pull the plug on this if it hits around 70 degrees. We'll see if it can stabilize. We'll be back. Alright, so after a good 10 minutes, let's go take a measurement here. And we find out, just wiggle this around a little bit, trying to find the hottest spot. Well, look, 45 degrees. So clearly this the setup here, maybe heat coming off that, but nothing major. So clearly the setup here can handle its full, well, the full output load of about 600 milliamps. Again, with an input of about 1 amp, and maintain its 1.46, pardon me, volt output. So that's pretty fantastic. So yeah, I don't see any issues with this whatsoever. Again, like I said, there's a bit of problematic with the output noise, but that's not a big deal. It's not a showstopper. We're going to do one last test. One of the primary things we want to find out when we're doing a switcher, especially with a switcher that's doing a boost from 0.6 volts to 1.5 volts, i.e. boosting a battery to give us a constant output voltage, is, well, what's the current consumption? How is the input current affected by the drop in battery not battery, but drop in input voltage, pardon me. So to that end, what we're going to do is we're going to measure this. Now I've set up a small setup here. I have a power supply which can be remotely controlled by a serial port. So I've written a small little program to control this guy and run it from down from 1.5 volts to 0.6 volts in 10 millivolt increments. And after adjusting the voltage, taking a current measurement, it's not going to be super accurate, but I don't actually have the means to measure with a decent multimeter in an automated fashion. So I just figured, well, we'll just do it this way. This will be good enough for the moment. So the setup's pretty straightforward. We have our electronic load again. It's set for 100 milliamp, and we'll do this. We'll do a couple. I'll probably do a couple of series of tests, but we'll do one which is 100 milliamp load through the range of input range of 1.5 volts to 0.6 volts, or down to 6.6 volts, and we'll see what the behavior is of our switcher here, and how we'll see what we're going to definitely see is we're going to see the current increase. So it's not magic, right? So as the voltage decreases, you can picture this being a battery or anything. In this case, it'll be just a power supply that's decreasing the input voltage, mimicking simulating what would happen in a real battery under load as the voltage starts dropping. And of course, this can source much more current. So what we're not going to be measuring is the behavior of the current side. So this is an ideal case, right? If we had a perfect battery that could source as much current as possible, even though its voltage dropped, we will end up still getting less performance that we're going to measure here. So this is the best possible case. As our voltage, our input voltage drops, our load is staying the same, constant. So what's going to change, of course, is our input current. So we'll see that go up as a function of the voltage, input voltage going down. And that's that. That's the setup. So I'm going to go ahead and turn on the load here, and I'm going to run the program. Take the measurement, and you'll see it start going right there. There you go. Now, unfortunately, I didn't know how to get rid of this display, because when you set the voltage, it switches to the limit view, and then it switches back to the measured view when you take a measurement. So it's a bit of a quirk with the actual power supply, or perhaps just my lack of understanding of how to program it. It's the first time I've actually created an automated test setup like this. So it should stop right now. There you go. So I'll shut off the load, and I should have a file of data. So I will go and crunch that and be right back. Okay, so here we have the data that we captured as part of our test of Butterizer. And let me just walk you quickly through the actual data here, and we'll then take a look at the chart. We captured two columns, or two sets of data. The first was the input voltage, and this is the set voltage. Input to the Butterizer is obviously the output voltage of the power supply, so this is what we set the power supply voltage to. And then this is what the input current that we measured that Butterizer was drawing from the power supply. The next two columns are the input power, which is simply a multiplication of these two columns together, and the output power, which, for the sake of the argument, since we assumed a constant load of 100 milliamps at a constant output voltage of approximately 1.5 volts, I approximated the output power here to 0.15 watts for the just for the illustration, but it's going to be close to this. It may have floated around, and indeed, as the input voltage dropped, the output voltage would start dropping too at some point further down. And after that, it was just a really quick efficiency calculation, which is simply the output power over the input power, and that gives us a percentage, or times 100 gives us a percentage. And with these pieces of data, we can sort of understand a bit about how a basic DC to DC boost converter works. So let's go take a look at the chart. I charted, as a function of the input voltage, both the input current as well as the efficiency. And you can see here, this is the input current. So as we start at 1.9 volts input voltage, we have an input current of approximately 150 milliamps. And that starts going up as we decrease the voltage. And of course, this should come as no surprise. The output current is constant, and the output voltage is constant. So, the equation has to balance. There's the input voltage and current is equal to some percentage of efficiency times the output power, or output voltage times current. So this should come as no surprise that if we're not modifying anything on the output, and indeed we're still forcing a constant power essentially of 0.15 watts, well, then the input, something has to happen on the input, and as we decrease the voltage, well, the current will increase. And this is a basic principle of how boost converters work. The top curve is the efficiency curve, and here's something that's more interesting, because now we're actually seeing the behavior and the performance of this particular switcher at a 100 milliamp load with a constant output voltage. And as we decrease the input voltage, we're seeing that we're going to actually get an increased efficiency up to just about 0.3 volts, 1.3 volts, pardon me, where we peak, and I forget exactly where that is, but it's something along the lines of 83 point something, 83.7 I think it is, 84.1 volts, 84.1%, and that is at an input voltage of 1.32 volts, drawing an input current of 1.35, 0.135 amps. And then from that point on, we decrease, and as we decrease the voltage with our constant output load, the input current increases and our efficiency drops. But again, we're only dropping to approximately, we start at roughly 68%, and we're only dropping all the way at the end to about 66%. So we could say on average that, the worst performance we have is about 66%. For a switcher, that's apparently not that fantastic, but in this particular case, it's really interesting that you can operate in this band right around here and have a fairly efficient, have over 80% efficiency, even down to something like 9.9 volts, I think it is.
Yeah, okay, so let's say 0.97, so about, just under 1 volt, you still get over 80% efficiency, which is kind of nice. So all in all, is actually a pretty decent switcher. It's got a max peak efficiency at 84%, and again, as all boost converters do, if the output power is fixed, then something's got to happen on the input side, and in this case, the input current is going up as the input voltage is dropping. So I hope that's helpful. Maybe gives you an idea of how these devices work and why they're kind of neat, and how they can extract that extra power out of a device, but only to a certain point. Because again, don't forget, this is a ideal. We used a power supply for this. This is an ideal voltage and current source, quote unquote. It's not a battery. When you have a battery, of course, hooked up to this, the ESR, the equivalent series resistance of the battery, the internal resistance of the battery, is going to increase, which is going to prevent you from the battery from being able to source higher amounts of current. So at some point it's going to cut out, because the switcher just can't draw enough current to feed this formula here that we have, which is that as the input voltage drops, the output current needs to rise. So there's a certain point where these 2 points are going to meet. And of course, the real way to test this would be to actually hook a real battery up and measure with the same setup, where we have a 100 milliamp load, with a constant voltage, so a constant power load, and measure the voltage of the battery as well as the current that is drawing, to measure that, and we could graph again the total power used, actually, even as a function of that. But for the moment, I'm going to leave it at that. I don't have the equipment to measure that, and it'll have to be left for somebody else to do.
The Butterizer. Thanks for watching. Hope you learned something. Take care.